Thank you very much. So I'm from Ed Nervicius group in Germany, and we are looking at cold collisions in the molecular beam. So how we start? We start with supersonic expansion. So this is a really simple process. So the process that we every day use in our refrigerator is like adiabatic expansions. So we have a really high pressure gas cylinder. We expand the gas into the vacuum chamber, and what we get? We get something super nice. So this is a thermal source, 300 Kelvin, and we get a really nice sort of Dirac delta at 1 Kelvin temperature. And but what is the problem over here? There is no free lunch. So they are really cold, but they're really fast. The beam is traveling around 500 meters per second. This is the neon over here. It's not sitting at zero velocities over here. So then how we cool the molecules to reach the lower collision energies. So we move to the inertial frame of reference. So how we do that? So we use the merged beam configurations over here. So we have two Ivan Levy valves over here. One beam goes really straight, and another beam we bend with a magnetic quadruple guide over here. And then we detect our molecules over here in our VMI velocity imaging setup that we show in the next slide. And what we can achieve over here, if we match the velocity between the two beams, we can actually reach to the lower collision energy, almost close to the zero relative velocity over here. And we can tune, in our experiment, we can tune the collision energy from starting from 300 Kelvin to the millikelvin regime. Okay. So why this regime is super interesting? Because so this is, you see, this is the cross-section measurements with the relative velocity. You see, this is a really boring regime over here. This goes down with the temperature, and suddenly at the lower temperature, we see some beautiful safe resonances over here. So this region is super interesting for us to look at this kind of tunneling resonances in this region. Okay, so this is our setup, sort of like a tabletop setup. Does not take much real estate over here. So what we do, the same thing, we have a magnetic guide, and how we detect our products. Now we detect the products in coincidence. So we have a velocity map imaging detector for the ion side, and also we have a velocity map imaging detector for the electron side as well. So we map both the electron and ions in coincidence. So how we do that? So we don't use this expensive relay line detectors, but we use something very simple technique. So we look at our ions and electrons from our CCD camera, and also we record the electronic signal in our DAC. So this is how then we correlate the one-to-one, the signal from the camera and from our DAC, and that's how we really do the coincidence measurements over here. So recently we solved the problem of our data analysis. It was a bit slow. So Julia Nervicius in our group, she really does this FPGA thing, and we can do all the analysis on the fly in the FPGA. Okay, so what is the motivation of looking at this kind of reactions? So this is all started because of the fantastic student Baruch, who really designed this coincidence apparatus for us. And what he studied over here, he started with the penning ionization. So penning ionization of neon with H2, and what it gives a H2 plus, so it has enough energy to kick off an electron from H2 molecule and gives an electron. And we record the H2 plus ions and the electron in coincidence. So what they see over here in this experiment here, like they start with the penning ionization product over here, and then the wave packet really decays to the different vibrational levels of your H2 plus. And this information is encoded in our kinetic energy of the electrons in the electron VMI side. And what happens after that? So depending on the vibrational state, it can have anisotropy. It can really goes to different channels of different vibrations and rotations. So this wave packet can really decay back to, depending on what is the open channel and closed channel, that can decay back to different rotational levels of H2 plus. So this is this is really the state-to-state dynamic that we see over here. So here you see the electron side velocity map imaging, and this is the beautiful ring that you see is really the vibrational levels of H2 plus molecules. And this is a really dirty picture of all the states that coincidence in our ionic VMI image. So this is almost 200 overlapping quantum channel. But with the help of the coincidence, what we can do, we can really look at only one state. So you can really look at V equal to 1, V equal to 2, and you can really do it all this in the state selective manner. So this is really cleans up all the picture for us. So this is what we saw in the experiment. This is really the distribution coming from V equal to 1. And this is for the H2 plus, and these levels that you see is really the rotational distribution of your H2 plus molecule in the final state. So these are the different J's. So this is the J7, J8, and this is the, you see the ortho, also the ortho para kind of distribution. So what next that we did? So with the collaboration with Christiana's group, they looked at the different potentials. So they tried to compare our experimental results with the different potentials that we got. So the CCSDT potentials was done by Marcus group from Basel, and these other two MRCI potentials at different basis sets was calculated, taken from these two papers. So what we see in the comparisons over here, so all the potential looks super fine to us. Everything looks super okay, and everything matches very beautifully to the experiments. There is nothing to complain. So what's next, but better we can do? So this is really the question that you're asking over here. So this is really the Feshbach levels for neon H2 plus that we populate in our experiments. And from there, it decays to the different rotational channels. So we really populate a very thin band of our Feshbach band, so just below our dissociation limit over here. And the orange one is our initial wave packet, and this is our Feshbach wave packet over here. They overlap quite nicely over here. So this is the signature we wanted to see in our experiment, whether we can see this signature in the final distribution. So that will be fantastic if we could see that. So how you can see that? So Christiana and his student Carl calculated all these things, and they say, what they say, so if you have to increase the resolution in our experiment, so it's not good enough. So now the resolution that you had in our experiment, you can really see this is the three potentials we are comparing. Three of them looks almost similar, but if you can increase the resolution in our experiment, at least let's say 4 times, which is realistic, but it's hard, then you can really start to see the differences in this kind of final state distribution. And if you could do 10 times, that would be fantastic. Then you can see really all the three potential surfaces actually looks very different when you see the final state distribution. So this is done for only one J state, J equal to 5. So okay, so we take that challenge. We take the words from Christiana, and what we try to do over here. Also, we wanted to move to neon HD. Why? We wanted to move to neon HD because this experiment was done over here at 2.7 Kelvin, the experiment that I showed before. And now we wanted to move to neon HD because there is a resonance over here which comes at 22 millikelvin, and it only comes from the one single partial wave. So it's p partial wave. So this is our structure of the Feshbach states that imprints in our final distribution will be less complicated over here if we do the experiments over here. So, but we initially didn't listen to them. We tried the experiment over here at 62 Kelvin. The only reason is super easy to do the experiment over here because it was done in a sort of small angle scattering experiments, and we had really high magnetic fields that disrupts our electrons, imaging, and then you have to put shielding, compensation coil, you have to work a lot. So we tried to do the experiment over here. And what do we see? Exactly similar picture as compared to the H2. HD also, we see really nice rotational state structure distributions over here for HD plus now, but all the three potentials behave very similarly, and all of them gives very excellent results. Okay, so now I think it's time to increase the resolution of our experiment, also move the whole experiment to the Mars beam experiment and do the everything very nicely. So now we went to the 22 millikelvin regime. Also, we increased the resolution of our increments almost 4 times. That's quite a lot of work we did, and what we see over here. So all long story short. So this is now you see the blue curve is the high resolution data that you get over here, and the red one is the low resolution data at 22 millikelvin. And you see super nice splittings over here for all the J states. So these are really the imprint of the Feshbach states that we initially populate that really comes on the final state distribution. So this is super funny. So this is the rotational levels of HD plus, and what we see over here in the splitting is the rho vibrational level of your triatomic molecule. That's really coming from the Feshbach states. So this is we call like spectroscopy without light in collision. Okay, so now we can compare the potentials. That's the whole idea of doing this work, going to the higher resolutions. Now you see that low resolution, everything looks super nice. If you go to the higher resolutions, we started to see the difference. So this is the CCSDT potential from the Marcus, and this is the other two potential. Maybe CCSDT doing a bit better than other two potentials. And if I zoom in a bit more at, let's say, J equal to 8, only one peak. This is at the higher, lower resolution of the experiment, and this is really the higher resolution of the experiment. Now you can start to see the differences in the potentials. So we are really happy with that. We also have reactive channels that are also activated after some time. So we have really a neon H plus and neon D plus also in the experiment, and we're going to also resolve the neon H plus and neon D plus in the experiment. And this is all you can do also in the higher resolution. You also see the splitting in the reactive channels as well. So this is also you can compare with the potentials. Okay, so something now I have 2 minutes. I want to speak about something that we are trying to do very recently. It's not in the abstract, so it's very new. So that experiment that I showed is very slow. So we run at 10 hertz. So it depends on how much current we put in our coils. So we record this data for almost 3-4 months. So one data set is really takes 3-4 months to collect. So it's really slow. So we have a lot of time to do the other experiments over here. So what we did, we built another setup. So we built another setup over here. So now what we wanted to study, we want to study the Rydberg and molecule collisions. So what we start, something simple without magnet. So we tried with 2 beams, similar, helium metastable, start with HD, and we come over here, we prepare the Rydbergs, it goes to the VMI chamber, we image with the low field and really image in our MCB detector over here. And we pulsed all the 8 plates over here. And what we wanted to see, so it looks like something like this. This is a super long time of flight tube over here. We wanted to make it very long because we want to enlarge the image. So this is how we prepare the helium Rydbergs now. So this is really 2-color. We started from the ground state. We have a discharge in front of the source. So it goes to the triplet P2 states, and from there, so we have IR 1083, and then from there we go to the different ND or NS states. So now we are preparing only the ND states. Okay, so now what do we expect? So you're looking at really the classical velocity map imaging. So elastic scattering, nothing complicated. So helium Rydbergs colliding with your HD molecules. So what do you expect? Yeah, some things like that, because you have one velocity, it can scatter, and velocity map imaging setup confirms. If you start with a single velocity, you reach to the detector at a single point. So you expect a single ring over here like that. Okay, and what we see? Diffraction oscillations. So this is really, you see this high low peak over here. So these are the diffraction oscillations. It's coming from really the Rydberg collisions, coming from the Rydberg atoms. So this is the angular distributions for the Rydbergs. This is the same plot plotted in angular. You can see the oscillations over here. So we are not the first people to see these diffraction oscillations. So they are seen very early in 1980s. This kind of reactions, and this is also seen in elastic collisions. Also, the very nice paper by Bass in elastic collisions over here. Very beautiful images. So this is all scenes over here, but now we are seeing this thing in the Rydberg experiments. Okay, so this is now in work in progress. We change the collision energy, and you can see the stripes really, number of stripes goes down as we decrease the collision energy, because less and less partial wave contributes to this thing. So we can really scatter from different quantum number, different state. We have a lot to do over here. We can play with the polarization, stark field. Yeah, we have a lot to do over here. Okay, so in the summary, so this is really the state-to-state dynamics, helps us with the better resolutions. Is now a test for potentials. Also, is the diffraction oscillation in the Rydberg atoms. I'll thank all the team. So these experiments are done by me and Yufang, and this is started with Baruch and all the theory collaborators. Thank you all.
Time for two quick questions.
Yeah, I actually have 2 quick questions, if that's okay. So first of all, for the Rydberg differential cross sections, you have this very pronounced backscattering. Do you think it's a resonance?
Yes, I think so. So this is really the, if you see over here. So if you have higher collision energy, this is this backward scattering over here that you see is really coming from resonance, and we see at the higher collision energy. If you go down, the collision energy is really getting smaller and smaller.
Did you map it, like integrating the?
Not yet,
okay.
Not yet. So this is we are not trying to do. So you have to scan the collision energy and really take the backward scattering and plot with the cross section. So this is the next we wanted to do.
For the metastable neon plus HD collisions or H2 collisions, you have this pronounced L equals 1 partial wave.
Yes.
Resonance.
Yes.
Do you see it in the differential cross section? The P wave?
In a metastable, no, because that is a sort of inelastic kind of experiment. So it gives a penning ionization products. So you don't see a partial wave over there.
Okay. The outgoing, there's too much outgoing energy. Okay.
Yeah.
Okay, let's thank Arijit again.
Thank you.